Hello students, so far we have discussed about the analysis of crystal structure through the analyzing of the unit cell of the crystal structure, and for that we have set 5 parameters what we have discussed in the last classes. In this class I would like to discuss about the X-ray diffraction by the crystal and the Bragg's law. The diffraction of X-rays as a tool for investigating the structure of the crystal, and this was first suggested by the German physicist Max von Laue. What he observed? He observed that when a X-ray beam passes through a crystal, at the opposite side of the crystal, if we placed a film, then we find that there are a large number of dark and bright spots. But Max von did not find the possible answer for that. That is, why these spots come inside the film, he did not find the answer for that. And in the meantime, W.H. Bragg, who was an experimental physicist, showed this pattern to his son W.L. Bragg. And for your information, for this study, Max von in 1914 got the Nobel Prize. And in this story, this is a story of father and son. W.L. Bragg was an experimental physicist and his son W.L. Bragg, William Lawrence Bragg, was a theoretical physicist. And there is an interesting story of physics that this W.L. Bragg, the son Bragg, who got the Nobel Prize at the age of 26 only, and he is the youngest Nobel laureate in physics. So what happened? Anyhow, W.H. Bragg, that is the father Bragg, got this pattern, and he also produced by himself through his experiment the same pattern by repeating the same experiment as shown in figure. He got the same pattern and he showed this pattern to his son and asked for, is there any possible reason for that? And W.L. Bragg took it as a puzzle to solve it. He investigated the condition for X-ray diffraction through a crystal using a simple model. What he thought? He thought that X-ray is nothing but the electromagnetic wave like the visible light, and when it passes through the crystal, there is a possibility of diffraction. And he found out a model to analyze or to explain this diffraction pattern. What he did? W.L. Bragg assumed that X-rays are reflected from the parallel atomic planes in the crystal. What he thought? That the whole crystal structure is divided into several parallel planes of atoms, and he assumed that when X-rays are incident on this parallel plane of atoms, it partly reflected from each plane. And he also assumed that there is a multiple reflections which interfere constructively in those directions. When incident rays are fall on the crystal planes, there is a multiple reflections are possible, and these reflected rays may interfere constructively to produce a bright spot if we placed a detector or screen here. And if we try to understand through this picture, we can explain the Bragg's thought through this picture. Suppose the horizontal lines, which are the blue lines here in this figure, represent the parallel plane of atoms which partly reflect the incident X radiation, and the distance between the two successive planes are d. Okay, and now the path difference between the two rays is 2d sin theta. What this mean? This means that if we say this is the ray 1 and this is the ray 2. Suppose that ray 1 incident along this direction and reflected along this direction, but when ray 2 incident in this direction and reflected from the second plane, and this will move along this direction, and we can see clearly from this picture that for ray 2 it has to travel more path than the ray 1. So we can see easily if we zoom in this picture that much path, if we say this is the point A and if this is the point O and if this is point B, so AO plus OB, that much path has to be traversed by the second ray more than that of the first ray. So there is obviously a path difference between the ray 1 and ray 2. And what is the path difference? Let's say the angle between the incident ray and the atomic plane is theta, and according to Snell's law this angle must also be the theta, and since the ray 1 and ray 2 are parallel, so this angle is also theta and this is also theta. So if this angle is theta, then this angle must be theta because this is 90 degree. What we have done, we want to find out the extra path. We have drawn perpendicular from the point, let's say this point is C, on the second ray, and this much is the extra path which has to travel by the ray 2. And from this simple figure we can see this is an isosceles triangle. For that this is the 90 degree and this side will be d sin theta because this is d, so this side will be d sin theta. Similarly this portion also d sin theta, hence the extra path, that means this path, this total path is d sin theta plus d sin theta. Therefore the path difference between the ray 1 and ray 2 is 2d sin theta, what I have written here. So the path difference between the two rays is 2d sin theta, that is the second ray travels more distance of 2d sin theta compared to the first ray. Now if these rays interfere constructively, that means after reflection, if there is a possibility of constructive interference, then according to the condition of constructive interference, we know that the path difference is the integer multiple of wavelength. Wavelength of what? That means the wavelength of the incident beam of light. So if these two interfere constructively, or in other words if there is a constructive interference, then the path difference between the two ray, that is the 2d sin theta, must be equal to the integer multiple of the wavelength lambda. So this is the condition for constructive interference, and in other words you can say this is the condition for the bright spots in the film. So if we use this condition, we will find that 2d sin theta equal to n lambda, where n equal to 1, 2, 3, these are the integers. So this is known as the Bragg's law of crystallography, and this is the further equation to analyze the crystal structure. And if we know this theta, because it is in our hand, so we can just changing the angle of the incident ray. Theta is known to us, lambda is also known to us. So if we know the first order or second order diffraction, that means if n is also known, then from this relation we can find the d, that means the interplanar spacing, the atomic planar spacing we can find out from this relation. So there is an important observation from this, why we have used the X-ray to find the diffraction when it passes through the crystal structure, why we don't use the visible light. So if we see from this relation, we can find that, as we know that sin theta, the maximum value should be 1, that is sin theta is less than equal to 1. So if we use this restriction on this equation, then we can also find that lambda must be less than equal to 2d. Now since d is near about 1 angstrom, that means the interplanar spacing for the most of the crystals are near about 1 angstrom, and which is about 10 to the power minus 8 centimeter. And if we use this value, we will find that lambda is less than 10 to the power minus 8 centimeter. So the wavelength, the value of the wavelength should be less than 10 to the power minus 8 centimeter to achieve the Bragg's condition. But this range is only possible if we use the X-ray, because the visible range of light is, the wavelength of the visible light is more than 10 to the power minus 8 centimeter. As we know from the, if we take the visible range, it is 400 nanometer to near about 800 nanometer. So this wavelength is greater than the wavelength lambda what we need to satisfy the Bragg condition. Hence diffraction pattern is not possible if we use the visible light in place of the X-ray, and that's why X-ray becomes an important tool to investigate the crystal structure. Thank you very much for your kind attention.